In this video, we are just going to talk about heat. So heat, we're talking about the exchange of thermal energy. It's important that you do not mix this up with temperature, which is related. Temperature is a measure of thermal energy. But they have two different meanings. So, as an example, if you think about if you have a cup of coffee and you set it out and it's normal room temperature. So, we tend to think of this as being about 25 degrees Celsius, depending on who wins the argument over the thermostat in your house. This may be a bunch of different temperatures, but they're all cooler than the temperature of your coffee to start out if you make a hot coffee. So if you set this coffee on the counter, you know that eventually that coffee will cool down. So the hot coffee cools to a lower temperature by transferring thermal energy to the surroundings. And there is a point at which it stops, right? At some point, that hot coffee has cooled down to the temperature of the room, and the reason that it ends up being the temperature of the room is just because your room is really massive in comparison to the size of your coffee. The point that it reaches, we call that thermal equilibrium. So this thermal energy transfers from the thing that has a high temperature to the thing that has a low temperature until thermal equilibrium is reached. And we know that we are at thermal equilibrium when the two things are at the same temperature. So in this case where we had, a tiny cup of coffee in comparison to a whole room, it ends up being room temperature. Now, when you touch that coffee, right, if you're to put your finger in the coffee to test the temperature, it feels cold to you just because it's lower than the temperature of your body. For things that don't have quite such large differences in mass, that temperature is going to be somewhere in between, right? The hot object will give off thermal energy, the cooler object will absorb that thermal energy, and the temperature will be somewhere in the middle. So when we calculate Q, it depends on that difference in temperature and the identity of the substance. So every substance has a different capacity for absorbing heat. We actually just call it the heat capacity. And there are a couple of different forms of heat capacity that we will use. Now, it'll always be a constant. It'll always be related to the specific substance, but there are some small differences in units that will kind of affect the overall equation in which we are using it. So just our generic definition for heat capacity, which we use a capital letter C for. It's the heat required to raise the temperature by 1 degree C. And you will see this version used for things that have really large masses, in that we don't take the mass into account. And a heat capacity will have units of joules per degree C. The specific heat capacity which will be C sub S. Well, it's the heat required to raise, most of this is going to be the same, heat required to raise the temperature of 1 gram of a substance by 1 degree C. So our units are joules per gram degree C. And then, you know, we're chemists, we like to measure things in moles, so we can also say we have a molar heat capacity. And I'm not going to rewrite this whole thing. It is the heat required to raise the temperature of 1 mole of a substance by 1 degree C. So this will be a C sub M, and its units will be joules per mole degree C. And you may even see these in per temperature units of Kelvin, but 1 degree Celsius and 1 degree Kelvin are the same thing, so those are often interchangeable. Just take a look at the units that you have and make sure that you're using the right one. So the equations that we use, if we have a generic heat capacity, we're looking at Q equals C delta T. If we have a specific heat capacity, Q equals M CS delta T. And if we have a molar heat capacity, Q equals N, because we need moles, times the molar heat capacity times delta T. So these are the 3 versions of this equation that you will use. So just to give you an idea of what these heat capacity temperature ranges are, not temperature ranges, value ranges are, here's some specific heat capacity values. For lead, it is 0.128 joules per gram degree C. For something like copper, it's 0.385 joules per gram degree C. And for water, if you want to know why it takes so much energy to heat up water, it is 4.184 joules per gram degree C. Okay, so let's do this. We have a couple of practice problems to do. We're going to do one quick one just to put some numbers and units in here, and then we're going to do one that's a little more complicated. So our first practice says how much heat is released by 240 grams of water as it cools from 96 degrees Celsius to 25 degrees Celsius. So we have a specific mass of a substance and we have a temperature change. And if we look a little bit earlier, we also have a specific heat capacity for water. So we want to calculate Q, and it is equal to M C sub S delta T. So this is equal to 240 grams times 4.184 joules per gram degree C. And then our delta T final minus initial, 25 minus 96. So the order of the delta T is vitally important to doing these problems because this is the part that ensures you get the correct sign for your heat value. So our water is giving off heat, so we should expect this heat value to be negative. And if we do 25 minus 96, we do get a negative value. So the heat value is negative 71295.4 joules. And unless I give you a specific unit to report this in, you're welcome to leave it as joules. We probably want to convert it to kilojoules because it's a pretty big number to be in joules. All right, so that's it for the first example. So then the question is, where does this heat go. And that heat goes from the system into the surroundings. So we will do many problems where we have to look at both sides of the heat transfer. And when we do this, we will assume that the two things transferring thermal energy between each other are isolated from everything else. To be honest, this is pretty easily to do with even something as simple as a styrofoam cup, right, which we would consider to be insulated. And most of the time, what we are looking at is taking, say, like a hot piece of metal and then putting it into a container of cooler water. So if we do that, right, we've got cool water and we have this piece of metal. And I don't know, we'll show this like the heat radiating off the metal, and then we dump it in the water. And what we end up with, we've got water, we've got our piece of metal. Our water is warmed up. Our metal is cooled down. And that thermal exchange stops when we get to thermal equilibrium. And that means that they're at the same temperature, right? So my T final for the water is equal to T final for the metal. And all of the heat that is transferred from the metal goes into the water, so the magnitude has to be the same, but one thing is giving off heat and the other thing is absorbing heat. So the main thing that lets us solve this problem is by saying that the magnitude of the heat for the metal and the water are equal, but their signs are opposite. And you can put this negative sign on either side as long as you put it in there, because it's, again, a key part of getting this problem to work. So let's do an example for this one. And this example says a 32.5 gram block of aluminum gives us the specific heat capacity, initially at 45.8 degrees Celsius, is submerged in 105.3 grams of water at 15.4 degrees Celsius. What is the final temperature of both substances? And now here it tells us you can assume that they are thermally isolated from everything else. This is something that you can generally assume for these problems. So I think one of the best things to start with is just make a data table for this type of problem. So we know that we have a piece of metal and it's at some temperature, it's going to give off heat. The mass of that metal is 32.5 grams. The specific heat capacity, which is given in the problem, is 0.903 joules per gram degree C. The initial temperature is 45.8 degrees C, and the final temperature is unknown. This is what we need to solve. The water has a mass of 105.3 grams. Now watch out, sometimes they'll give you this in mils, and then you just use the density or assume a density of 1 to get out of mils and into grams if that's what you need. Or maybe take it the next step and get to moles if you're given a molar heat capacity. Thankfully, we get to stick with a specific heat capacity here, which for water is 4.184 joules per gram degree C. The initial temperature is 15.4 degrees Celsius, and the final temperature of the water is unknown, but one of the key things that lets us solve this is that these are equal. So the final temperature on each side of our equation will be the same variable. So we just need one equation. We are only going to have one unknown. And that, combined with knowing that the heat of the metal is going to be equal to the opposite, the heat of the water, is everything that we need to set up this problem and solve it. So if the heat of the metal is equal to the opposite, the heat of the water, then we can actually just set up mass of the metal times the specific heat of the metal times the delta T of the metal. So let's put an aluminum in here for subscripts, equals the opposite, the mass of the water, the specific heat of the water, and the delta T of the water. So I'm going to set these in for algebra purposes. I'm actually going to leave my delta T's without that initial temperature, and you'll see why. It just makes the algebra easier to deal with, and then we'll plug in those initial temperatures closer to the end. So I'm starting out with 32.5 grams times 0.903 joules per gram degree C delta T aluminum equals the opposite of 105.3 grams times 4.184 joules per gram degree C times the delta T for water. And so if I combine these terms, let's get this down a little bit, 29.348 delta T aluminum equals negative 440.58 delta T water. Now that I've dealt with all of those other constants, I can plug in my initial temperatures. Oh wait, not even yet. Let's do one more step. Let's get rid of these coefficients. If I just divide both sides by the 29, we can get this down to delta T aluminum equals negative 15.012 delta T water. This is even better, because now my delta T aluminum is T final minus 45.8 equals, I still have my negative 15.012, and then for water, it's T final minus 15.4. So I still had to deal with this, but now I only have to distribute through one set of parentheses and not through both. So T final minus 45.8 equals negative 15.012 T final plus 231.19. Now I can combine terms, and 16.012 T final is equal to 276.99. My T final is 17.30 degrees Celsius. And so this is where you can ask yourself if the answer makes sense. So first, this temperature is lower than the initial temperature of the metal. Right, it's lower than the initial temperature of the metal, and it's higher than the initial temperature of the water, right? So we did actually meet somewhere in the middle, but I mean, you'll notice it's actually much closer to the temperature of the water than it was to the metal, but that's just because of the very high heat capacity of the water in comparison to that of the metal.